Hello, everyone. Welcome to today's webinar, which is about writing engineering specifications with NBS Chorus. Chorus is a fantastic tool, and I'm hoping that today we can get to showcase some of this for engineering specification. A little bit about NBS and Hubexo, our company. Our mission is to use our unique data, insights, excellent software solutions. We can allow our customers in the construction industry to enable them to sell more, improve their efficiency, and build more sustainably. Today's webinar then. The webinar will last somewhere between 45 and 60 minutes, depending on questions. Attendees, please ensure your microphones are muted, and you will get the opportunity to ask questions using the dialog box on your screen, and then we'll follow up with those answers to the questions after this session. Okay, so please don't be shy with your questions. Okay, so what we're going to be covering today. Well, at last year we had a similar webinar, and it went down really well. We got lots and lots of feedback, but in amongst that feedback, there were a number of engineers that said, well, what about us? And there was a sort of a sense that it was quite architecturally focused. So hence the reason for today's webinar. We want to reach out and show actually that the power of NBS Chorus and the content within it that's really geared towards engineering-based specification. Okay. Our presenters today will be providing guidance on how to prevent engineering specifications in NBS Chorus. And they're going to focus on structural and civils, but also some MEP content as well, okay? And from them, you'll get a few hints and tips on how to apply best practice principles across these disciplines. And they're going to show examples from both our CAWS, Common Arrangement work sections, and our Uniclass 2015 content sets. So without further ado, I'll introduce you to today's speakers. First and foremost, we'll have Daniel Orsi, who's a structural engineer. Following Dan, we'll have Martin Hunt, who's a civil engineer. And finally, we'll have Ian Ezzy, who is a building services engineer. He's a mechanical engineer to trade, but he's going to cover MEP. A brief note, please stay connected. There will be lots and lots of links at the very end of this webinar. Please use those links. They're great resources. And please ask questions at the end of the session. So without further ado, I'd like to introduce you to my colleague, Daniel Orsi, who's going to give us some guidance on best practice specification for engineering disciplines.
Okay, thank you, Jason, for the introduction. I'm going to briefly provide some context for best practice before Martin and Ian follow on with some real-world examples. And what we're going to cover today is relevant no matter the type of specification, whether it's an early outline spec during the concept design stage, a performance specification for contractor designed elements, or a complete prescriptive or proprietary specification following the technical design stages. So very briefly then, why do we write specifications? Well, we want to convey technical information. We want to demonstrate design considerations and thought processes, and demonstrate compliance with codes of practice or legislation. We want to communicate the design intent to the rest of the design team, the contractors, the client, and any other stakeholders, to make sure that all parties are aware, aligned, and understanding of the project requirements. And finally, we write specifications as a form of risk management by making sure that all areas of the design are covered comprehensively. So why do best practices matter? Well, the consequences of a poorly written design specification in the world of structural, civil, and services engineering can be substantial, particularly if the project is complex and high risk. So where the consequences of failure are high, it's important to manage these risks. So some of the risks inherent to the design and construction phases are shown on the screen now. And the text highlighted in red are risks that a specification can directly influence positively or negatively. So we have technical risks in the form of material defects, construction risks such as poor workmanship or deviation from erection or performance tolerances. We have environmental risks such as corrosion, economic risks such as unexpected costs or delays. There are legal risks in the form of disputes or non-compliance. And finally, human risks, which could be misunderstandings or lack of oversight. So, a robust, well-written specification can serve as a means of proactive risk management, which by allowing the designer or the engineer to communicate technical information, which is comprehensive and detailed in proportion to the project. And robustness is a key concept in structural and civil design, and it's implemented in the core of the Unicode approach. Um, this is a different form of robustness, but the point I'm making is that specifications form part of the design. They can be the input criteria of the design or the output of the design. So it's important they are as comprehensive as the design, technical design itself. What are the key principles or criteria to consider when writing an engineering specification? First of all, we have design responsibility. We need to clarify roles and responsibilities and define who's responsible for design, execution, and quality assurance. We need to consider integration and coordination with other design disciplines. And this ensures that nothing is overlooked. We're reducing ambiguity and misunderstandings by increasing collaboration with the wider design team. Next, we have conformity and compliance. We need to demonstrate due diligence in the design by ensuring compliance with up-to-date design codes and legislation. An example given here for structural timber used for construction in the UK must comply with the CPR and be strength graded and marked in accordance with harmonised standard BSEN 14081 Part 1. So failure to specify compliance requirements may lead to the procurement of a non-compliant product. So in doing so, we're protecting against liability and we're ensuring that the legal and regulatory compliance. Procurement is another key principle. We need to identify procurement legislation and government policies and specify responsible and sustainable sourcing requirements. We can control product and material quality by defining these sources and requirements for conformity and procurement. Another example from timber, which should comply with the UK timber procurement policy and originate from an independently verifiable, legal and sustainable source. So we're preventing material shortcomings and we're reducing environmental risks and risks to legal and regulatory compliance. Another key principle is performance. We need to think about identifying system or product performance requirements and specify minimum aims with regards to structural, fire, environmental, energy, or other performance criteria. There's a fire example given here for exposed timber joists to have a reaction to fire to BSEN 13501 Part 1 Class B or better. So in this instance, the joists would require flame retardant treatment, which would be specified in addition to this. So this provides clarity of the design intent. We're reducing misunderstandings and oversight. We're reducing technical, economic, and legal risks. And just as importantly, we're ensuring that the systems or product are fit for their purpose. Next, we have quality and grade. It's important to be clear on the required quality or grade of the product or material that we're specifying. So this could be the minimum strength class of concrete or the bonding quality of structural plywood. So in doing so, we're ensuring structural integrity, we're reducing the risk of material defects, and we're protecting against liability. it's important to define characteristics. We need to identify product or material characteristics. What do we want the product or material to look like in terms of geometry and appearance? Are there any finishes required or treatments? Is there an intended design life or service environment which defines the durability requirements, such as corrosion protection, waterproofing, or fire protection? And are there any color density or consistencies needed? Two examples given here are consistence class of concrete and the preservative treatment of softwood timber. So defining the characteristics within the specification, it's avoiding misunderstandings. We're eliminating unexpected costs by getting rid of, reducing the risk of material defects and durability risks. Standards. A common issue in specification writing is referencing out of date or withdrawn standards or industry guidance. So we need to stipulate the use of relevant up-to-date codes of practice or industry guidance. And this ensures currency and compliance with the latest standards and regulations. We're reducing technical, economic, and legal risks by doing so. Moving on to the erection and erection stage. So we have workmanship. We need to detail requirements and restrictions on workmanship, site work, material handling, and processes. We need to identify any compliance obligations. A simple example is given here for truss rafters, which are to be kept vertical during handling and storage. So a very simple instruction within the specification, but we're increasing collaboration with the contractors, and in this instance, we're avoiding damage to the trusses. So we're ensuring accountability, we're reducing oversight, and we're avoiding material defects and unexpected costs. We're also protecting the designer, client, and contractor by documenting agreed upon deliverables. Next, we have erection and installation. So we need to identify requirements for execution, assembly, installation, and integration. We need to specify details for method and sequence of work, and detail any requirements for temporary works. An example given here is concrete should not be placed in adverse weather conditions without prior agreement with the concrete supplier or designer. So failure to mention this in the specification might lead to the concrete being installed in adverse weather, which may lead to defects or disputes. So we're increasing contractor collaboration, we're ensuring the correct installation, and we're avoiding defects and unexpected costs. Tolerances are an important principle to include in our specifications. We need to establish performance and construction tolerances. We need to define limits in performance testing or permissible deviations in geometry and setting out. And in doing so, we're providing a level of quality control. We're reducing construction risks, and we're avoiding cumulative errors that could compromise integrity. Next, we have testing. It's important to specify any testing and recording requirements for material quality assurance or performance validation and regulatory compliance. We must specify frequency and type of testing, and offer clear targets and benchmarks. A couple of examples here are cube testing of concrete and pressure testing of pipe work. So in specifying testing requirements, we're verifying the performance of our product or material, we're ensuring safety and quality, and we're detecting defects early on in the process. Similarly, inspection. We have to identify inspection requirements during construction and installation. And a common example given here in the timber industry is regular inspection of bolts, which may become loose due to the nature of timber. So instructions like this within the specification ensure materials and workmanship meet expected standards. We're enhancing safety, and we're avoiding defects and the risks that come with them. And finally, we have verification. So are there any obligations to provide evidence? We need to identify requirements for dimensional installation or performance verification, and specify submittals such as declaration of performance, certificates of compliance, or test reports as previously specified. So mentioning verification in the specification, we're confirming that materials and workmanship meet expected standards. We're ensuring compliance, enhancing safety, and avoiding defects and reducing the risks that come with them. So in summary, before Martin and Ian expand on these points, consideration of these key principles when writing the specification will help ensure it's comprehensive and robust, and ensures effective communication of the design intent. We need to include all the relevant criteria for the system, product, material, or process being specified. And I'm now going to hand over to Martin.
Okay, thank you very much for that, Dan. Firstly, a quick reference back to underscore the underlying context for best practice specification in Chorus. To begin with a quick heads up really for those who haven't seen it, and a reminder for those that have, there's the best practice specification guide webinar hosted by my colleague Stephen Hamill in recent months. That focused on the guide, which is split into 10 sections, and each of these covers one aspect of best practice specification. The sections here highlighted in bold above, that's namely classification and specification structure, design responsibility, and specification reference codes, are all particularly focused on specification writing. And they're actually themes that underpin the following webinar slides, which focus on communicating technical information via the Chorus platform. So they're worth having at the back of the mind as this goes through various examples. So if we go back to the key principles of engineering specifications as outlined by Dan, we'll now look in more detail at how some of these are covered for civil and structural engineering in a Chorus specification. As shown on previous slides, there are four main areas that these engineering principles break down into. There are too many to go over in the time available, so those highlighted above are the ones that we're going to focus on the following slides. So that is design responsibility and procurement within the general requirements, quality and grade, which is normally dealt with in products and materials, workmanship, which obviously typically forms part of execution, and then testing, which is one aspect of quality assurance at the end. The slides that follow will use the common arrangement of work sections content, although similar principles and techniques can be used with Uniclass content. Ian is actually going to look at Uniclass content a bit later on the mechanical side. G20, which is timber sections, has recently been updated and revised and is due to be republished in the coming weeks. For the purposes of these slides, the existing version of G20 has been used. That's to avoid any confusion. And it's been used to illustrate the key specification principles that we've highlighted here above. So I'm now going to move into demo mode, and the next few slides will show a series of videos that highlight these various different key principles of engineering specification. The first here is design responsibility that comes under the general requirements. Our first key principle under the general requirements is that of design responsibility, shown over here on the left of the slide. This typically requires specifier consideration of things like who has responsibility for parts of the work. In this case, the contractor is to take responsibility for truss rafters within the timber package, although clause 120 down here provides an alternative if, for example, the whole structural timber design is to be provided by the employer's engineer. The specifier also needs to consider how the decisions being made fit with the wider structural and civil design requirements, this area here. If, for example, somebody else is to do the design of any foundations, this would be outlined elsewhere away from the timber package in section B50 for general structural requirements. The scope of the contractor's design portion may also be described at high level in the preliminaries, in this case CAWS section A30. Thirdly, under design responsibility, the specifier needs to think about what the structural design requirements actually are in this area here. In this instance, the contractor is to complete the design, say in accordance with Eurocode 5 for timber design and PD 6693 Part 1, recommendations for the design of timber structures to Eurocode. But these items will be set out in section B50 for general structural requirements, this area here. In this example, there are also some clause items made available for the specifier to say something about what type of design information is expected back from the contractor. So drawings showing the truss geometry, for example, and when information should be provided. In this case, it is already set out in preliminaries information elsewhere. This cross-referencing to the preliminary section A31 in these bottom two items within Chorus helps to avoid duplication and confusion and also mitigates the risks of something being overlooked. The inclusion of clause items for type of information and timings is quite common across the civil and structural CAWS content. Here we have procurement, which is also part of general requirements. Under general requirements, we also have procurement as a key principle of best practice specification for engineers, again shown at the left-hand side of this slide. To address procurement considerations, the structural engineer may need firstly to identify legislation or government policy and incorporate this into the specification. In this timber procurement example from G20, the UK forestry standard can be included and the clause adapted to allow for this. This can be added in here, and these two sub-items then parked as they're no longer needed. Secondly, as with procurement more generally, provision of documentation is often a key feature. So on most structural timber projects, it is likely that some form of evidence will be required. Once again, adaptation of the clause allows the specifying engineer to set this up to suit their individual project. Here we add in an item about licensing and again park the sub-items as they're now no longer needed. Finally, procurement for structural engineers typically encompasses some form of certification and verification, and in this instance with timber procurement, identification of an appropriate chain of custody scheme at the bottom of the specification, down here. For example, the Forest Stewardship Council or the Grown in Britain scheme would normally be considered best practice. In this instance, this is covered here in the drop-down options, so we will select from the list and that completes the clause. Under products and materials, we look at quality and grade. The grading and quality of products and materials used in civil and structural engineering is one of the key principles of engineering specifications. For structural engineers, this could mean specifying a steel grade based on the minimum yield strength, whilst for civil engineers, specification of, say, a Type 1 granular subbase might be one part of ensuring quality control on a job. Usually, grading, quality and strength requirements are covered in CAWS civil and structural engineering content as part of the wider product or material characteristics forming another of the key principles of engineering specifications shown on the earlier slides. However, there are some examples in the content where specific clauses have been developed that are focused solely on grading requirements. Typically, these are cases where the specifying engineer is likely to have more detailed or involved information requirements. One such example is clause 160, grading and marking of structural timber, which is included in G20 timber framing. It's referenced there on the left-hand side of the slide. Following republication of G20 in the coming weeks, this clause will allow for specification of grading of timber to BSEN 14081 Part 1, the standard for strength graded structural timber shown at the top here. It will also allow for the addition of timber marking arrangements, as shown in the example here, requiring adherence to BSEN 14081 Part 1, alongside existing clause items down at the bottom here covering moisture content requirements. For execution, although wide-ranging, we focus on workmanship. Execution covers all key principles for a best practice engineering specification that are to do with the construction phase, where the specifying engineer has an interest in how something is put together. For example, this could be to ensure that a level of performance is met as a result of construction operations being carried out in a certain way, or that something has been erected in a certain sequence to avoid eccentricity of loading, for example, during installation. Execution includes workmanship, which also sometimes requires input on the part of the specifying engineer to make sure that performance of the structure is suitably calibrated for the operational phase and is not subject to undue deterioration during the project lifetime. An example of workmanship requirements specification covered in G20 is clause 450 for moisture content, highlighted here on the left. By giving due consideration to workmanship as part of the specification, the engineer can reduce misunderstanding and lack of oversight, help avoid undue project costs, and ensure the correct strength, stability and durability are achieved when natural processes such as drying out take place. In this example here, if clause 450, it's largely pre-filled, but the tightness of the information can be improved to make this more robust and make the expectations on the contractor clearer. BM Trada Wood Information Sheet for Moisture in Timber covers the moisture content service classes set out in Eurocode 5. So by adding this information in, this will adhere more closely to structural engineering best practice. We can do that by switching this new information in at this point here. And finally, this last one for service class 1. And under quality assurance, this is focused on the testing principle of engineering specification. Our last group of principles to consider for a best practice civil and structural engineering specification is quality assurance, which includes inspection and verification, as well as testing, which will be the focus here. Testing is covered in a range of different places within the G20 timber framing CAWS section. This includes clauses for moisture content testing and component testing for things like portal frames and glulam timber structures. Clause 480 in G20 is for truss rafter testing, and this can be used by the structural engineer to include for some of the provisions in BSEN 14250, which is a product standard for prefabricated structural members. By specifying this standard here, this allows the engineer to reduce risks on larger projects and point towards type testing as a means of achieving conformity. So we'll add that in at this point. The structural engineer is also typically concerned with early detection of defects in order to ensure safety and quality and help minimize risks to program, amongst other things. This is addressed here by including specific details on when tests are to be carried out and by identifying the purpose of the tests in the specification. So this is of importance in terms of the frequency and when tests will be performed, and the specifier can add those in here. So we'll have 10 tests at random. And in addition to this, we can also include in the specification the rationale for testing in the first place. Finally, test reports and timely submission of these are essential for confirming performance validation. I'm now going to hand over to Jason, who has some questions on specification and civil and structural engineering content.
Okay, thanks, Martin. Let's get a couple of questions around civil and structural engineering specification then. First and foremost, what do we do for these type of specifications at whole building level? How do we cover it? You've shown some individual sections around timber. What do we do at whole building level, guys?
I'll answer that if that's all right. So basically, Jason, we do cover higher level requirements. In CAWS, we actually have a section B50, general structural requirements, and that is typically where higher level whole building type requirements for structural information can be included. So an example of that would be that in there is a clause 10, I think it is, information to be provided with tender, or there's also a clause for ground investigation report. So it covers civil and structural type items in there, but at the more wide-ranging level. You've also obviously got the prelims as well in CAWS. I'll just highlight those where, at a very early stage, you can have information of relevance. Over across in Uniclass, which Ian will be talking about shortly, things work slightly differently. The same, if you like, raw information is there as is in CAWS, but typically more of it would be found in the Uniclass equivalent of prelims, which is what we call the project management sections. So such as PR30. These are like the Uniclass equivalent of the preliminary information. So you would find the same information, just at slightly different levels in there.
Fantastic. Thanks for that, Martin. Another question I had that maybe I could get Dan to expand on this is, what do we do about testing for structural concrete? Something like compressive strength test, cube test. You showed that. How do we do it, Dan?
So typically in CAWS, concrete cube testing is covered in section E10, I think it is. So section E10 should be used to specify the requirements for cube testing, whether it's clause 508 specifies the testing, when it should take place and how frequently. Clauses 520, 530 and 550 cover the testing itself, and they specify the accredited laboratory that should undertake the testing, and any requirements for testing results, and guidance on what to do if cube tests fail or are non-conforming.
Excellent. Thanks so much, Dan. Okay, thanks very much, guys, for your presentation and the answers on those questions. I'd like to move on to Ian now, who's going to look at MEP specifications for us.
Okay, thank you, Dan, Martin, and Jason. I just wanted to take the opportunity to provide some additional examples in the mechanical engineering world of some of the key principles that Daniel and Martin have already outlined. I'm going to show a couple of examples here of how a specifier can utilize our mechanical content to ensure the compliance both of their products and of the broader systems. In the first instance, I'm going to demonstrate this with some new content we have authored relating to multi-purpose medical pendants. Clearly, when we're specifying, we want to ensure that we are specifying compliant products or systems. And the first step in that is to understand what it is we are trying to comply with. Now, typically for systems in particular, that may well be the building regulations, and we'll look into that. For products, however, there will be different sets of regulations depending on the particular characteristics of the product and the uses to which it is going to be put. Within the general guidance provided in Chorus, we will typically offer a section on compliance with regulations. You see here it's general guidance 2, so we click on this, and this will provide additional explanation as to the particular regulations that this product, multi-purpose medical pendants, needs to comply with. For instance, the supply of machinery safety regulations, medical devices regulations, electrical equipment safety regulations, electromagnetic compatibility regulations, and potentially pressure equipment safety regulations. Furthermore, we provide brief explanation as to the mechanism by which manufacturers can demonstrate compliance, and that is typically through the use of harmonised in the EU or designated in the UK standards. These are technical standards which have been approved by the relevant governments as being a suitable mechanism to demonstrate that a product has been manufactured in such a way as to meet the essential requirements of the particular regulations. Typically, it is these harmonised or designated standards that we provide as a suggested value within the general standards drop down. And we'll see here, for instance, that we have BS EN 60601 and BS EN ISO 11197, which are the designated standards for multi-purpose medical pendants. And we'll click that there. With systems, the responsibility for ensuring compliance falls more on the designer or the specifier rather than the manufacturer. Typically, to demonstrate and to ensure compliance, you would start by referring to the relevant regulations, for instance, the building regulations, and then move on perhaps to the sort of technical guidance documentation which exists, such as the approved documents to the building regulations, which are home to more technical guidance that specifiers can use. And these approved documents, for instance, will then perhaps cite more detailed standards. In particular, I wanted to demonstrate this from the perspective of fire stopping in, well, I'm using natural gas supply systems as the example here. Now, ensuring that your system complies with the relevant regulations may require specific knowledge of the regulation, or at least adherence to a suitable technical guidance document which is recognised as ensuring compliance with the regulations. This doesn't tell the whole story though. Sometimes the relevant technical guidance documents might not provide quite the level of detail that's required to ensure compliance with the specific regulation. And an example of this is the approved document B, proposed solutions for the fire stopping of service penetrations. You'll see we're still in our natural gas supply systems clause here, still in our authoring environment, hence the different format that you won't be familiar with perhaps. What we're looking at here is actually the clause item for pipe sleeves. Now, before we go any further, we do make the distinction between pipe sleeving for the protection, the physical protection of pipe work, or pipe sleeving to prevent the accumulation of leaked gases in, for instance, a wall void or any sort of interstitial space. However, we take it a bit further by referring the specifier to our general guidance, and specifically our fire performance general guidance, where we go into more detail about the requirements of approved document B. So I'm just going to click onto another window here. Typically you just navigate to the general guidance from within the clause. And you see here that the general guidance on the right hand side of the screen talks about service penetrations and compartmentation, specifically precluding ventilation systems, which as we probably all know are different beast altogether. The point we make here is that we initially refer to the approved document, in this case approved document B in England or Scottish Technical Handbook 2, either domestic or non-domestic, and the various regional variations in those. We describe the process by which the resistance of a compartment is tested and classified. Now, this information isn't as explicit as it could be in the approved document. And the danger there is that whilst faithfully following the solutions that are proposed in the approved document, you may still stray into a non-compliant scenario because you haven't specified a product or system which has been appropriately tested or certified. And in particular, the sleeving detail, specifically where it is used for fire stopping, requires some additional specification detail in order to ensure compliance with the building regulations. Simply following the detail as it is set out in the approved document may not be sufficient. And this is just an example of how we try to assist the specifier in ensuring compliance through our clause items and our general guidance. In the next video, I wanted to demonstrate the use of the Chorus platform when attempting to specify design responsibility at different levels, be it with the contractor, the designer, or a specialist manufacturer. And I'm using our newly authored Blackwater reclamation content for this demonstration. I've chosen to demonstrate the different levels of design responsibility using our new Blackwater reclamation content. This is particularly useful content for this demonstration as these products and systems may involve a variety of contractors on site and also piecemeal responsibility for the design of the systems and the product. So it's important to ensure that there are no gaps or omissions within the specification. So here I'm showing a descriptive specification clause for a Blackwater reclamation system, the intent being that the designer specifies the required outcomes, but the contractor designs the systems. So it's important right at the top of the clause that we define the design parameters for the system. We're also defining what we require from the controls and basic stuff like how we expect a designer to size pipework. The next section is particularly relevant to Blackwater systems, where it is important to define the extent of the Blackwater system in particular, where it interfaces with the above ground drainage systems, where it interfaces with the building cold water supplies, and where it interfaces with the distribution system. And this is a distribution system specific to the reclaimed water. You can see here the part clauses all relate to more specific design criteria or characteristics, and I'll look at those when we go into our prescriptive specification clause. And then down at the bottom here, a specific or an important scope gap which could arise with Blackwater systems is who designs and installs the interconnecting pipework between the different items of plant. This is maybe common also to the likes of modular chillers, modular boilers, perhaps even heat pump installations where the manufacturer does not provide a prefabricated pipework jig of sorts. So I'll just demonstrate quickly what we're doing with the design parameters clause. This is the performance clause, which lays out or sets out how we wish the Blackwater system to perform. And in particular, for instance, we're defining, well, what are the sources? Where is the water to be treated coming from? What are we going to use the treated water for? And indeed, what quality do we expect the water to be treated to? Now here we're just referring specifically to one line of guidance from the relevant British standard. However, if we had more exacting requirements, let's say for instance we might be using the treated water for laundry purposes and we require low or zero colour, we can actually break that out here at the bottom here. We have color, and I'm actually going to free type 0 just to be extra demanding of the plant manufacturer. So that's an opportunity to go over and above what is set out in the British Standard, and we'll save that. Now we talk about descriptive plus or a performance spec with additional preferences defined. So that is very similar to our descriptive clause. However, we are actually defining the modular plant that we want installed. Perhaps you have a particular manufacturer in mind, or somebody you have been working with during the early stages of the project. Within the modular Blackwater reclamation plant clause, we are now defining the performance we expect from the plant. Now this entirely overlaps with the content of the previous performance clause, so we've now omitted the performance clause up here because that performance is defined within the plant. And you see it's all very similar stuff. Again, we've just used the one-liner from the British Standard. However, we could break it out into bacteriological parameters and non-bacteriological parameters. Otherwise, it is a very similar clause. I've also taken the opportunity to show where perhaps a client, a designer might have a preference for stainless steel tanks or stainless steel equipment skids. You can define that within this, what we call descriptive plus clause. And the final type that we've discussed in the previous slide was, of course, a sort of traditional prescriptive specification clause. In the case of Blackwater reclamation, it might require a fairly brave designer, certainly in these early stages of Blackwater use in the UK, but we have emphasised this in the general guidance that within treatment plant guidance, it is a specialist discipline, and specifiers are advised to consult with wastewater engineers or water hygiene specialists. At this stage, we would anticipate most people using the packaged treatment plant clause item. However, this is your opportunity to set out every specific piece of equipment that is required for the Blackwater reclamation system. Because we have set out all the equipment, it is sort of presumed that the designer, who is also in this instance the specifier, they know the performance requirements, and these are inherent in the selection of the equipment, which is also scheduled elsewhere. So we've actually removed these performance clauses. However, as is typical with most service installations, we've left the controls performance clause in here because that is more often than not a contractor design portion, and as such the performance needs defined. However, the nuts and bolts, if you like, aren't specified in this clause. The final two characteristics I wanted to demonstrate were the specification of the performance of a product and where the specification of particular physical characteristics of that product may actually overlap with some of the performance that you have already specified. And I'm using our heat interface unit content to demonstrate these principles. So I wanted to use our recently introduced heat interface unit product clause to demonstrate some of the characteristics you might wish to specify. Now clearly, if you have a preferred product and manufacturer in mind, I've used Vital Energy here as an example and their V-Therm standard HIU, then that's the first thing you would specify. And you would hope that that would effectively lock in the particular characteristics of that product. However, as we've probably all experienced as a project progresses, there may be instances where people have valid reasons for maybe moving away from this particular product or model, and it is very useful to have the desirable or the required characteristics of this product defined further down, or specified rather. So as we move down into the product characteristics, the first section is typically related to the performance of the product. Now, you might argue that the first few items underneath duty here are duties rather than performances. This is kind of getting into semantics a little bit. But the item I wanted to highlight was the volume weighted average return temperature, or VWART, of this particular unit. Now, I'll not go into the technical background of VWART here, although you can see that our general guidance does just this. But by specifying the VWART, you are in effect specifying a particular, shall we say, efficiency of the heat interface unit. And this might mean that further down, where we get into sort of physical or product characteristics of the unit, you might not actually need to specify. So for instance, the domestic hot water control valve and the space heating control valve, I've currently left these as manufacturer's choice, and the reason for that is that the particular specification of these valves may only be relevant as it pertains to the VWART. For instance, a 2-port thermostatically actuated control valve may not be able to deliver as low or as desirable a VWART as an electronically actuated pressure-independent control valve. So by selecting an electronically actuated PICV, I'm perhaps guaranteeing a low VWART, and in fact I might then choose not to even specify this. I'm trying to park the item, there we go. So that's an example of where a performance characteristic and a physical characteristic might be interrelated. You could of course specify both, giving yourself an even tighter control over the final choice of unit. And with that, I was going to hand back to Jason, who I believe had a couple of questions on the mechanical and electrical content.
Thanks so much for that, Ian. Some really interesting and important stuff there. Some questions. Ian, MEP systems, they typically have lots of interfaces. They've got interfaces with other systems. They've got interfaces with building structure, building fabric. How do we capture those in Aspec?
Yeah, absolutely, Jason. Maybe two useful interfaces to discuss are fire stopping. I mentioned that earlier there, which especially these days should really be considered as a system in its own right, and we have content to that effect. And we even make it clear within natural gas supply systems that you wouldn't specify the fire stopping within the natural gas supply system clause. You would specify it within, for instance, the pipe collar fire stopping systems clause. Now, what's really good about this is, of course, if the mechanical specifier didn't want to take ownership of the specification of the fire stopping system, we can, of course, share the project and the specification with other design team members, allowing the relevant expert to specify within the same specification. Another very brief example of that might be within my favourite Blackwater reclamation systems clauses. We talk about the controls for the Blackwater reclamation systems. Now, controls are a reasonably typical example of something that might be a contractor design portion, or at least a specialist design portion. And again, we can insert a specific system clause for water supply control systems. And you see here that links back to our Blackwater reclamation system controls parameters clause. And this is the home for perhaps your controls engineer, assuming they are invited into the project specification. They can then use this clause. So this allows the interface between different disciplines.
That's really interesting, Ian. And I think the important thing there for me is that the collaboration. We're multidisciplinary in any project now, and that ability to collaborate is so important. So thanks for sharing that. Ian, you demonstrated some performance criteria in one of your product clauses earlier, and it's really interesting because where we're able to select, we've got an idea of what product we actually want. It must be really tempting to just say, give me that product or equal or approved, and not bother to set performance criteria. Can you underline the importance of why we still ought to underline performance criteria, please?
I'm sure both the other guys have got examples of this too, Jason. Yeah, I mean, equal and approved, define equal. At the end of the day, you will have selected a particular product for a reason, and you really want to outline that reason straight away. Otherwise, it can still just become a free-for-all. If somebody were truly specifying an equal product, it would be the product you had already asked for. Otherwise, it probably isn't equal. But a more sort of human example of that is where you may have developed a relationship in the early stages of a project with the product manufacturer or designer, and that could become key to the project. And if they were to suddenly lose that specification, if that specification were to be broken, you may lose valuable relationships. You may lose valuable information or expertise. And that's one of the things that you maybe even can't specify unless you really lock down the specification of that product with the criteria.
Interesting. Dan, Martin, any thoughts from your realm on that subject?
Just to reinforce there what Ian had said, that on the civils and structural side, it's that the key really is having that specification, as he put it, nailed down. You're looking to avoid, let's call it, unnecessary substitution as far as possible, and that's a key component on the civils and structural side as well as on the MEP.
Certainly is. No, look, thanks guys, and I think an important point raised there. All right, well, look, just to summarize to today's webinar, I think some key points for me are that we've seen that NBS Chorus is definitely for the whole design team. It's not just for architects. You know, it's really powerful as a tool for engineers, and I hope that's come across today. A really key feature is around collaboration. It's so important that, you know, where we've got multidisciplinary teams, we're able to collaborate with architects, engineers, and specialist, specialist contractors, etc. It's really, really powerful to invite those people onto specs, and it really helps you to get that cohesiveness in your spec and really button your spec down. So that's been a key thing for me today in that. Okay. What I would like to show you very, very briefly is that we've got some links. As I said at the top of the presentation, there's some really good links, not least to this presentation, but we do have some sample specifications. You can click the link on this and you can go and look at those samples. They're really, really useful. They give people ideas of how to do things and how we want you to approach things at NBS. Certainly, there's today's webinar, as I've said. You can also get to rewatch the webinar, so you can watch the recording back if there's anything you'd need to look at. There's also the guide that Martin referred to earlier, you know, the best practice specification guide. Some really, really great stuff in there. And again, look, it's not just for architects, it's for everybody. So please get a look at that. And finally, you know, if you're a prospective customer or you're a customer who's thinking about, you know, changing library, please reach out to us. You can book a demo of Chorus, and again, there's a link here attached. So please, you know, if you want to do that, click the link. All that's left for me to say is thank you so much for watching, and please, you know, reach out, and if there's any other questions, reach out to us. I'm sure we'll be happy to speak to you and get you some answers. Thank you so much.